Hi guys, so I'm going to review the sketch notes that you should have already taken. We're going to start with the beginning, move on to the Ed puzzle, and then to the atom. So you do not need to change your notes to make them look like mine, but you should add to anything new that I go over that you don't have in your notes. So in the beginning, we learned that everything in the universe was once in this tiny little, very hot, very dense area. And there was this explosion 14 billion years ago, and we call that the Big Bang. From the Big Bang, all these particles, some particles were becoming annihilated, but what was left were positively charged particles, neutrally charged particles, and there were some negatively charged particles. The positively charged particles, we call those protons, and the neutral ones are neutrons. We've already learned that from the sketch notes or the Ed puzzle that we watched with electricity. Shortly after the Big Bang, 3 minutes later, the positively charged particles and the neutrally charged particles started to combine. And those two particles are about the same size. And once it got cool enough for the negatively charged particles, the electrons, to join the protons and neutrons, which were in the nucleus, they became an atom. So the protons and neutrons are in the nucleus, in the center of the atom, and those negatively charged particles, the electrons, are going really, really fast around the nucleus. And they're moving so fast it almost looks like a cloud. So kind of like if you take a picture, if you've seen a picture of somebody running, if they're running really fast, but you can see the trees, for example, in the background, they're perfectly in focus, the person running looks like they're blurry. So that's kind of what, if we took a picture of an atom, what the electron cloud would look like. It's just a big blur because they're moving around super, super fast. So here's a picture, an example of an atom once that all three of them join together. And the atom is the building blocks of all matter and everything in our universe. So matter is what stuff is made of. And this is important. This is going to go on to our story box, because once the Big Bang happened and there's all this matter, all these atoms now in the atmosphere, they're moving around because of the explosion, and they're starting to gather. So anything that has matter has mass, and it would create gravity. And we learned in the story box that there is this grid. And when there is anything that has matter that is causing gravity, that grid bends just a little bit. So we learned that dust and gas create gravity. When there's enough of the dust and gas in one area, because the gravity attracts things. So once enough dust and gas attracted to each other, it really starts to bend that space that it's at. They group together and they start colliding. And the more that it bends, the more gravity there is. And they start colliding and start creating the sun. And remember that gravity is the force that pulls all objects together. So once we have the sun, there are still some particles left over. And those leftover particles are continuing to, the sun, remember, has a bunch of gravity. So the sun's gravity is pulling those particles in toward the sun, but they're also moving. So they are just kind of spiraling around the sun. They're moving from the force of the Big Bang. And as they're spiraling around, they're starting to collide into each other. So this is the leftover dust and gas that did not make it into the sun, start colliding into each other. And those eventually will become planets. So when they smash into each other, they first form the planetesimals. So they're smaller versions, they're just objects, like bigger versions of dust and gas particles put together. Then they continue to collide into each other, and they become protoplanets. They're very close to planet size, but they're not quite they're not a sphere yet. The gravity did not pull it into a circle yet. But when some more of the dust and gas continue to collide together, eventually we will get our planets. So the planets have to fit certain criteria. They have to be massive enough to make its own gravity, make it round. They have to be orbiting a star, and there cannot be any other clumps in the path. If there's more clumps in the path, they will collide and add to that planet's mass. All right, so I'm going to demonstrate. And the reason this is important, the reason why I wanted you to watch the planet Storybots episode, not because we're learning about planets, but because we're learning about atoms and what happens in the sun to make bigger atoms. So I'm just going to give you a demonstration here. So in the Storybots episode, we saw them have this grid, and I made my own representation of the grid. And we can see that it's kind of even checkered, just like the grid was. And if I put one single tiny little marble, we can say that this represents the dust and gas. I'm going to just put it right in the middle. I don't know if you saw the material move just a little bit, but it's pretty level. So it doesn't have a lot of gravity. It doesn't have a lot of mass. It's one little marble, but it is enough to bend space just a little bit. So when other dust and gas particles are in its path or close enough to it, they will be attracted to each other. So then we have some more dust and gas in the path. And more. And we can see, can't really see on the video, but we can see that they're coming together, they're joining together because of gravity, and the material is actually starting to bend. When we have enough colliding together, we actually end up with our star. So here is our star with a lot of mass. I'm going to make the star, we know the star is the biggest part of our solar system, so I'm actually going to make it really massive. So I'm going to put two bigger masses in the middle, and I'm going to show you, once the star is formed, we have more dust and gas particles still moving around, and you can see that as they're moving around, they're starting to collide into each other. And they become a planet. And we know, you guys have been taught about planets for many, many years now, so you know that planets orbit the sun. They go kind of, not a perfect circle, they go more in an ellipse shape. And you'll see why. So from the Big Bang, from that motion already, the planet wants to go in a straight line. But now the sun has a ton of mass. It has a ton of gravity. So the sun is pulling the planet toward it. So that combination of wanting to go this way and being pulled this way creates that spiral. Eventually, because we are on Earth, this demonstration will all end up in the middle because gravity is stronger on Earth than the gravity that I'm creating here. So eventually everything gets pulled to the middle because the gravity of the Earth is pulling it down. But you can see it's not going in a perfect circle and how it is spiraling around. So this is how planets go around the sun. But it's also how, like I said, it gives you a visual of how atoms are made. So if we start with one tiny little atom, and the gravity, so this is what's happening in the sun, most of the sun is made up of hydrogen atoms, which are the smallest atoms that we have, or helium atoms. What's happening is the gravity of the sun is pulling these atoms together so forcefully that they are combining and creating a bigger atom. So one hydrogen atom combined with another hydrogen atom will have a mass of 2 protons, or not a mass of 2 protons, but would have 2 protons in it instead of 1 proton in it, which would make it a helium atom and no longer hydrogen, which is the next atom up. 1 helium rather, and 1 more hydrogen combined would be 3 protons, and that would be lithium. So that's how we started to get these bigger atoms. I just wanted to show you so that you kind of have more of a visual representation. Okay, now we're moving on to the atom. And we discussed a whole lot with the atom sketch notes. But I want to make sure that you really understand certain parts of this. So one really important part is how to read the periodic table, those boxes inside of the periodic table. And we have here, we always will have a small number that is a whole number. That's usually at the top. These boxes can be arranged differently. Sometimes this number would be to the side and this number would be up at the other side. Sometimes just the symbol and the name are rearranged. But as long as you know what they all stand for, it doesn't matter which way they are ordered. You should be able to read and understand what it's telling us. So this first number tells us how many protons. This is called the atomic number, and it tells us how many protons there are in the atom. So like I was demonstrating before with the grid, one hydrogen atom would have one proton plus another hydrogen atom. When they combine from smashing together from all that force from the gravity of the sun, this would become two protons, and we no longer have hydrogen. We have now moved on to helium. I'm going to grab a periodic table so you can see what I mean with that. So here we have hydrogen, and then two protons would be helium. So if we have the two helium, so we have one helium plus one hydrogen, we would then get three protons, which like I said before, would become lithium, and so on to get those bigger elements. All right, so the letter, usually it's one letter or two letters. The first letter is always capital. The second letter would be lowercase. If there is three letters, it would be a man-made element. And the two following letters would be, the two second letters would be lowercase. The first letter is always capital. And that would be the symbol. This would be how we are representing it. This would also be how we would write our chemical formula. And then we have the name. And then the last important number is the atomic mass. If it is a decimal, it is the atomic mass. So what that is the average of the samples of all of the isotopes that we have. And I'm going to go over the isotopes in a minute so that you understand why we have a decimal there. To find the neutrons, the number of neutrons, it's not just straightforward. So we know the number of protons is the atomic number. This is how many protons there are. We also say that this is the number of electrons. We just say that this is electrons because that would be a stable atom and they cancel, they kind of balance each other out. The number of protons is positive, the electrons are negative, and we want to have the same number of protons and electrons. So they would be equal to each other in a stable atom. But we did learn that electrons can flow from atom to atom when we're talking about electricity. So electron number can change, but we're usually going to just be talking about a stable atom. So we're going to have the same number. The atomic mass is the number of protons and the number of neutrons. So remember when we talked about the beginning sketch notes that I just went over, the first two things that joined together were the protons and neutrons, and that made up the nucleus of the atom, and that's the atom's mass. The electrons are so small that they don't make up the mass of the atom. So they are not included in this atomic mass number. It's kind of like if you step on a scale, I find my weight, and I don't know if I said this before, but you find the weight, and then you step off and you pull off a piece of hair. The hair would represent your electrons. You get back on the scale, your weight hasn't changed. So it doesn't really matter that how many electrons there are, because the mass won't change. The protons and neutrons is what would affect the mass. So to find the number of neutrons, if we know how many protons there are, and we know what the number of protons plus neutrons is, to find the neutrons, we just need to get rid of protons. And because this is a plus, to get rid of it, you would just subtract it. So we would take our atomic mass, which is right here, And if I rounded this number to the nearest whole number, this would be a 1 because it's 1.0. So if I look at the second number and it's below 5, I leave the number the same. So 1.0079 would round to a 1. And I subtract the number of protons there are, because this is protons plus neutrons, subtract my protons, which is 1, and I'm left with my number of neutrons, which would be 0. So usually there are 0 neutrons in a hydrogen atom. However, we do have that 0.0079, and I'm going to explain where that comes from in a minute. So we have two different numbers that we're looking for when we're talking about the mass of an atom. We can either talk about a sample, which is where this decimal comes from, and that would be the atomic mass. And then the atomic number would be for one particular isotope of that atom. So when we're talking about isotopes, let's look at that first to understand the atomic mass and the atomic number. Let me go back. All right, so we have carbon. You guys should be very familiar with carbon by now. Carbon has been something that you should have learned a lot about in 7th grade, the carbon cycle. In order for us to get energy, we eat something called glucose that plants make, and the glucose is C6H12O6. If you didn't know, that C is carbon. So we are consuming carbon constantly, putting it into our bodies, but the form that we are consuming is an isotope C14. So in our bodies, as long as we're alive, we are replenishing that C14. So we have that C14 in our body. However, once an organism dies, whether it is a plant that did photosynthesis and makes its own glucose, or whether it is an animal that consumed glucose, that C14 can no longer be replaced. We can't consume the glucose anymore. We can't put that C14 in our body anymore. So what happens is this is an isotope that is not stable. It wants to break down. It wants to be C12. That's where it's happy. So every about 5,000 years, this is where half-life comes in, which is why you did the half-life after this, half of the C14 breaks down into C12. So why is that important? That tells us, it gives us the ability to be able to identify how old a fossil is, or how long ago something was alive on the planet. So we would take a sample of the fossil, for example, and see how much C14 there is and see how much C12 there is. And we would be able to we know what the half-life of C14 or of carbon is, and we'd be able to say, okay, so it was alive this many years ago. So just to look up here again, so our C12 or C14. So remember, the atomic number cannot be different for the same element or the same atom. So carbon has atomic number of 6. So that means the protons have to equal 6. No matter what the mass is, the protons have to equal 6. So what would be different? Remember, electrons don't even count. That's like the hairs on your head. So the other mass that would affect the mass would be the number of neutrons. So for C12, 6 plus what equals 12? 6 plus 6 equals 12. So the neutrons for C12 would be 6. The protons for C12 would also be 6. Over here, C14, protons has to be 6. Neutrons would be 8 though, because 8 plus 6 is equal to 14. So this is where the isotopes come in. Then we take a sample. So for example, carbon, the picture that I gave you for your sketch notes was a diamond and an atom when I was talking about the atomic mass versus the atomic number. So the atomic number, remember, would be one sample of the carbon, so just one particular atom, where the diamond would have a whole bunch of different types of isotopes. So maybe it would be C12, C13, and C14. We would have more C12 than we'd have 13 and 14. But what we do is we take the percentage of the C12, the percentage of the C13, and the percentage of the C14, and then we could figure out what the atomic mass is, and that's where this decimal comes in. So the sample that I gave you was about neon. So in the world, for neons, we have neon 20, we have neon 21, and a mass of neon 22. Neon 20, there's the most of. We have 90.48% of neon 20. So that isotope of neon, we have 90.48%. For the isotope of neon 21, that just means there's a mass of 21. Neon has 10 protons. So that would be 10 and 10. 10 protons, 10 neutrons. This would be 10 protons, 11 neutrons, and 10 protons, 12 neutrons. So for neon 21, we'd have 0.27%, and for neon 22, we have 9.25%. So we would multiply to figure out how much of neon 20 there is, and we get 18.096. Multiply this, we would get this number, and then we multiply these, and then we would add these numbers together, and that's where our atomic mass comes from. So these are real-world samples, real-world numbers of all of the isotopes of that particular atom, and that's where that mass comes in. Hopefully that makes a little more sense. If you guys don't understand it, please ask. So up here again, for the atomic mass, that's what's in the box. That's what's given to us because these are real-world samples. But if we're talking about one particular atom, we would have a specific isotope of that atom. So our atomic number would be a whole number. So for example, C12 and C14, my atomic number would be 12 for C12. My atomic number would be 6. My mass number would be 12, the mass. And then the atomic number for C14 would still be 6. Atomic number would still be 6. But my mass number, not atomic mass, not the average, but the mass number would be 14. So hopefully that makes a little bit more sense with your notes. I hope that you added to any of the notes that you needed. But I did explain, so one real world example of why we would need to know isotopes would be to identify fossils, like I explained over here. Another one would be to identify and help save elephants. So to help protect the elephants against poachers, we can figure out the isotope in their hair of nitrogen, how much nitrogen there is of either N15 or to compare to N14, and that would tell us what environment the elephants are going to be in, so that way we could help send patrols out to make sure that the poachers don't go to the elephants and don't kill the elephants. If you guys have any questions, please make sure you ask them. Hopefully this makes a little bit more sense and that you added to this, because this is very important for our big project that is coming up.